Okay, welcome back. Our first speaker today is Nick Trefethen, who's Professor of Numerical Analysis at Oxford. Going to tell us about the AAA algorithm, which nobody can deny is the top algorithm alphabetical.
Hi, so I saw most of you yesterday and the day before on Zoom, and I'm sorry I couldn't be here, but I'm delighted to be here now. I won't say a lot about Nick, but one thing I can say is that I've known him forever, since he seemed much younger than me. And the hardest decision I ever made in my life was whether or not to move to England 25 years ago. And he was a part of the attraction of England, and he's also a part of why I'm glad I moved. It's been wonderful being in the same numerical community as you, Nick. Okay, so I have or so. It's a talk about rational approximation, and the idea is, suppose we had a black box that could do rational approximation. Well, the AAA algorithm is more or less that. And in fact, I'm not going to tell you anything about how it works, partly because there isn't time, and partly because, in principle, any other black box would be fine also. There's nothing I'm going to show you that really depends on AAA. It's just that until recently, we haven't had this kind of fast black box rational approximation algorithm. I should mention there are a bunch of people in the room that know a lot about rational functions, and in particular, Stefan Göttel is, he's your man. So he's been an expert in rational functions in all applications since his undergraduate era, I guess. And so Stefan is really an incredible resource in this area. Okay, so the talk is going to consist of, well, it's called 10 examples of AAA approximation, and they're numbered from 0 to 16. Here's the code. I'm going to run them all and just spend a minute talking about each one. As I was chatting beforehand, the algorithm is about 5 years old, but actually in the last 6 months or so, I've become to appreciate how many different things you can do with rational approximation, more than I think I knew. So hopefully these examples will show you a bit of that. I'll begin by setting up some abbreviations. And then example 0, which we call warm up, is just showing you a typical way that you can approximate a function. So in every case, it's sort of like the Good News Bible, where the words of Jesus Christ are in red, you know. So the call to AAA is always in red. And you can see the standard format is you call AAA with some function values and then the set where those function values live. So you apply it on a discrete set. In this first example, it's a set of 50 points on the unit circle. And what the plot shows is the poles of the AAA rational approximation. You can see the error on that set is 10 to the minus 15. That's the maximum, of course. And most of the codes have a pause command. So in this one, if I press return, you then get some error contours, 10 to the minus 0, 3, 6, 9, 12, 15, showing, as approximators know, that when you approximate on a set in a real or complex set, interesting things happen in other parts of the complex plane too. Saf and Varga know a lot about these poles. And by the way, in each case, I've mentioned somebody who's relevant to this particular problem, ranging from Alan Turing to Heather Wilbur. Let's see, the next one is approximation to high accuracy. So this is for Nick, who has taught us all more about floating point arithmetic than we knew before. This one's called rounding. And what this code does is it just takes e to the x on the unit interval sampled in 500 points. And the reason for so many points is I want to show you the detailed behavior of AAA at each of the points. So here we have 500 dots from -1 to 1. We've computed a rational approximation to e to the x. And you can see these are the errors at each of these 500 points. And the red line, so easy to plot in MATLAB, it's kind of fun, shows the smallest possible error. So you couldn't possibly have a dot between the red lines because floating point arithmetic doesn't have any numbers there. So you can see this vanilla flavored call to AAA gets quite close to optimal accuracy at every point. even though we're making no attempt to get a truly optimal approximation. Now, rational functions are famous as a technique for finding poles. So the next example, called Gammaplot, takes 30 points on the unit interval as our sample, and it just samples the gamma function at those 30 points. And then it plots the resulting rational function on a wider domain. So you can see that it looks like the gamma function. Familiar effect in rational approximation, even though the data is only here, it obviously figures out about these poles, but it also finds out about this pole and even this one. It doesn't know about all the other poles because its goal is only to approximate here. If you look at the numbers, you can see that 0 has been identified as a pole to really full precision, -1 to about 12 digits, -2 to about 5 digits, -3 to 1 or 2 digits. The next one is called Analytic Continuation, and this really is Alan Turing. So, you know, if the Riemann hypothesis had been false, it would have been Alan Turing who showed that. He really did numerical computations with the Zeta function in the 30s, regrettably did not find any zeros off the critical line. Anyway, Zeta fun. If you look at the code there, you see it takes 100 points on a vertical line in the complex plane, and the real part is 4. The reason for 4 is it's very easy to evaluate the Zeta function if you're well in the right half plane. You can do it in one line of MATLAB. So there you have the Zeta function evaluated at 100 points. And then when I press return, it does the AAA approximation and then plots a phase portrait, so-called, of the result. So the colors represent the phase of a complex function. Red is positive, cyan is negative, and so on. Looking here, if you know your Zeta function, you'll recognize that this is just what it looks like, but it's only a rational approximation, so it doesn't capture it back there. The zeros are all nicely lined up there. The pole at 1 is there, and so on. If you actually look at the numbers on the left, you can see that a lot of the zeros are 0.5 to many digits just from this simple rational approximation. The next example is in honor of Yuji. Is that Yuji? Yuji is on the hallway with me, and we've done many things together involving rational functions. So the next one is called 2 disks. And in this case, we just take 2 disks in the complex plane, each sampled with 100 points. And the function that we're working with is -1 on one of them and +1 on the other one. You approximate it with AAA. And here are the poles of the approximation. Notice there are a few bad poles there, and we know how to remove them, but I won't go into that now. There are the error curves. So as usual, you get your 15 digits on the approximation set and then interesting behavior in between. And if you look at the phase portrait of that, you can see this is basically a branch cut separating one branch of an analytic function, namely 1, and another branch of an analytic function, namely -1. The next one is Don Huybrechts and I are currently writing a paper on this one. It's the business of approximation from equispaced data. So if I type equidata, you'll see here is an analytic function sampled at 40 equally spaced points on the unit interval. Now, you know, approximation from equally spaced data is a problem. You certainly can't use ordinary polynomial interpolation because of the Runge phenomenon. In fact, if you do use ordinary polynomial approximation, there's your interpolant of degree 39 with terrible inaccuracy near the boundary. So there's a big literature on what to do beyond polynomial approximation, and AAA is actually the best method we know. So there you see the AAA interpolant. It's accurate to 11 digits. And incidentally, in ChebFun, it's a routine matter to convert that to another polynomial. So this is the minimal degree polynomial, degree 39, terrible error. This is a higher degree polynomial, degree 104, another interpolant, accurate to 11 digits. The next example is called beam. So most of these examples are not in the linear algebra terrain because I can't compete with Fran and Stefan and the rest of you. But this is an example from Paul Van Duren's NicoNet set. Where's Paul? Who actually cooked up this particular example? Is that you? Or? No. Oh, really? Okay, I didn't know that. Anyway, this is we're plotting the norm and the resolvent on the positive imaginary axis for a matrix of size 348. And then if you approximate it by a matrix of size 20, you get, obviously you've captured the important stuff, but there's a lot of 328 degrees of freedom down low. The next one is something I've worked on a lot in the last few years. The code's called clustering. One reason rational functions are so important is that they can resolve singularities, branch point singularities, and the cost is only root exponential. So you get convergence at the straight line if you plot it against the square root of the degree. So here we're approximating the square root of x on 0, 1 with this beautiful root exponential convergence. And if you look at the poles of the best approximation, they're exponentially clustered near the singularity. So there's a lot of beautiful mathematics here. Where's Micah Meyer? She's also, there are lots of people in the room who've done related things here. The next example is called spline node. So this one comes from Heather Wilbur. It's about resolution, finding singularity. So here we have 11 data points and a smooth function between them, but it's actually a spline. So that's a cubic spline. Now, it looks smooth to the eye because we can't detect the discontinuity in the third derivative. But if you approximate it by AAA, you find poles in the complex plane near these knots. Isn't that beautiful? So the poles are exponentially clustered near each knot. Interestingly, there's of course no poles at the endpoints because those are smooth, but there's also no poles at the penultimate and second point because those are the so-called not a knot condition. And I'd forgotten that about splines. When I did this, I was confused. Why are there no poles there? Until I remembered that the default is the not a knot condition. The next one's called branch cut. So here, if you look at the code, you'll see that there are 500 random points in a square in the complex plane. And the function we're dealing with is the square root of x minus x squared. So there's a branch point singularity there and another branch point singularity there. And then if we do our AAA approximation, you can see this beautiful curve of poles, which is a rational approximation to a branch cut. And Micah Meyer worked on this, and the great expert was Herbert Stahl. The next example just comes from last week in Poland. I was talking, there was a great talk by Anna-Karin Tornberg. And here the issue is, how do you extend the data, smooth data beyond some boundary? So here I've got a domain, and I'm about to show you some smooth data in there. And I've sampled it for convenience on radial lines. So there's the data. Now, this is not an analytic function. It's a real analytic function, which means you can extend it along lines, but you can't extend it along surfaces because it's only real analytic. But then we use AAA to extend it along each of these 100 lines. So we're doing real analytic continuation along about 100 different lines. And it's really cool. This is competitive with the methods she was showing us based on radial basis functions and so on. You can see that you can cross the boundary and get a couple of oscillations successfully, and then eventually the analytic continuation from the rational function ceases to be accurate. So we think this might, in certain contexts, be a practical method of extension across boundaries. The next example is something I've done with Abhi Gopal that actually originates with a visit to Anne Greenbaum in Washington. So this has to do with conformal mapping, which is one of the really cool applications of AAA approximation. So here we computed a conformal map by methods unrelated to rational functions, but then having computed the boundary correspondence from the blue to the blue, we then represented in that direction and separately in that direction by rational functions. So one rational function of degree 39 represents it that way to 6 or 8 digit accuracy, and another represents it in the other direction. This happens to be a smooth domain, but it even works with corners thanks to that root exponential effect. And if I press return, so what it's done is it's just mapped 1,000,000 points that way and then back again. So 1,000,000 random points forward and back, or backward and forward. That took less than a second to map 1,000,000 points back and forward, and the maximum error 10 to the -5. The next example is the least interesting visually, I'm sorry to say, and it's also the one where I know the least. But anyway, I have to do something with functions of matrices. So here we have a Nikium problem. We have a matrix with a bunch of eigenvalues, and knowing the eigenvalues, I've just sampled in 100 points or something around there. And I was trying to find a really crazy function to compare against. So what did I pick? I can't even, it's something ridiculously complicated. Anyway, one way to do it is with AAA, where you do rational approximations in these blue points, and that turns the f of a computation into backslashes. The other way to do it for this example is to use xpam and square root m and log m, which happens to take longer. That's not very significant, I think. But I'm making no particular claims about this example, merely that rational approximation is one of the techniques that is definitely in there when we talk about functions of matrices, as Nick, of course, very well knows. Example 13, here's another subject I know nothing about. So there's a review paper by Fran and Stefan and lots of other experts in the room, I think, about nonlinear eigenvalue problems. I've done nothing on nonlinear eigenvalue problems. So I just picked one of their favorite examples, where it's a 2x2 matrix. Actually, I'm sure you guys have noticed it could have been a 1x1 matrix, but that would have been really embarrassing. So they made it 2x2. But anyway, it's a nonlinear eigenvalue problem, and we know where the eigenvalues are. In this case, I guess sample the determinant. It's only a 2x2 matrix at a bunch of points. And then amusingly, these red dots in this case are the zeros of the rational approximation, zeros of the determinant. So you can see inside the sample region, it's quite accurate. Although at the origin, there should be a double zero, which is ill-conditioned, and sure enough, it has split into two. Next example is called Lorenz. So one thing that's fun to do is extrapolate from real solutions of ODEs into the complex plane. And I guess Marcus Webb probably, you did some stuff on this, didn't you? So here we've just computed a bit of a trajectory of the Lorenz equations, and we then give that as data to AAA. And so there you see in the complex plane, the poles of the AAA approximation to that curve. And notice how the poles tend to be along the gray lines where the curve has its extrema, because those are the points where the singularities in the complex plane are the nearest. Is Anastasia Keisel here by any chance? No, she's on maternity leave, but she's the one from whom I've learned a little bit about Wiener-Hopf splitting. Not a subject I know a lot about, but in complex variables, a very, very big theme is behavior of functions across intervals, curves, boundaries of all sorts of things, and many, many aspects of this. Wiener-Hopf is one, the Plumel formulas, the Sikotsky formulas, as they're called, the Hilbert transform, the Dirichlet and Neumann map. These are all related ideas that involve how analytic functions on one side of a boundary match up with their counterparts on the other side of the boundary. So Wiener-Hopf is one of the things in that space. And this example isn't graphically very interesting. What it does is it takes the function e to the minus absolute x, which is a standard test function, and it uses AAA to approximate that on the real axis. And then these are the poles of the AAA approximant. And from those poles, you can separate into, these poles correspond to a function analytic in the lower half plane, these poles to a function analytic in the upper half plane. That's Wiener-Hopf splitting. So AAA gives you a method for doing that splitting, and you can see that in this case, it got an accuracy of 10 digits. And then the final example is called L-shape. And this I owe to a typical pandemic colleague that I've never met. He's called Stefano Costa. He lives in Piacenza, Italy. we have yet to meet, but we've written a paper together. So here is just a taste of elliptic PDEs with AAA approximation. So we're facing the problem of solving the Laplace equation in an L-shaped region. And Stefano's idea is to simply approximate the boundary data with AAA. You get some poles inside and some poles outside. And then the idea is throw away the poles inside and use the poles outside as the basis for a partial fractions expansion to numerically solve your problem. And sure enough, it works. It's amazing. So this is now a very cool general method for solving at least the Laplace equation. And that's all I have to say. So thank you very much.